Algebra 3, Chapter 6, Section 5, Graphs of Other Trigonometric Functions. We're going to start with the graph of the tangent. Remember that it can be written as the sine of x over the cosine of x. And what that means is that every time the cosine of x is 0, the tangent is going to be undefined. So we're going to have some vertical asymptotes in our graph of the tangent. In fact, the graph of the tangent function is, like I said, will have asymptotes values. So here's what the graph looks like, and you'll notice we have asymptotes for the tangent at pi over 2, and then again at 3 pi over 2, everywhere where the cosine of x would be 0. The period for tangent is pi, which is also the distance between each asymptote. So for tangent, the period's different. Sine and cosine, remember, were 2 pi. Tangent goes through everything within pi. The domain is all real numbers except odd multiples of pi over 2. In other words, pi over 2, 3 pi over 2, 5 pi over 2. Or in the negatives, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc. The range is all real numbers. To draw the graph, you're going to locate the key points, which are going to be the x-intercepts and the asymptotes. It's also a good idea to locate a point on each side of the middle, which is generally your intercept, and in between the intercept and the asymptote. It's a good idea to locate those, and it helps you draw the graph a lot better. To find the vertical asymptotes, you can take, for the equation, y equals a tangent bx minus c, solve bx minus c equals negative pi over 2, and bx minus c equals pi over 2, and that gives you the asymptotes for a translated function. Cotangent is very similar, except with cotangent, every place where the sine of x is 0, the cotangent is undefined and therefore has vertical asymptote. Notice it also looks kind of like it's the backwards version of the tangent. Our asymptotes, well, first of all, our period is pi, just like tangent. That's the distance between each asymptote in a regular graph. The domain is all at real x except multiples of pi and 0. So as you see here, negative 3 pi, negative 2 pi, negative 1 pi, 0 pi, 2 pi, 3 pi, and so forth. Those are going to be where our asymptotes are on the graph of cotangent of x. The range, like tangent, is negative infinity to infinity. And again, like tangent, you want to locate the x-intercepts and the asymptotes, and getting a point on each side of the x-intercept is a good idea as well. To find the vertical asymptotes when the graph has been translated, solve bx minus c equals 0 and bx minus c equals pi. To get the graphs of secant and cosecant, what we actually do, weirdly enough, is we start with the graph of sine or cosine, and then we go from there. For example, at any given x value, the secant of x is the reciprocal of cosine. So the easiest thing is to actually graph the cosine first. Now, when cosine of x is 0, the secant is undefined, and when the sine of x is 0, the cosecant is undefined. So we're going to have vertical asymptotes in both of these as well. So here's what we're going to do. We're going to take and start with the graph of sine or cosine, then take the reciprocal of each y value, and what we get looks like this. So here's y equals sine of x, and then notice we've got vertical asymptotes going through where the sine hits the y-axis. And our cosecant is like little u's and n's that go to meet the sine curve. So the purple part is the cosecant. So it's the easiest thing to do for these is to actually graph the sine of the function and kind of get that in as a preliminary sketch and then use that to draw the cosecant. Cosine is the same way. If you graph the cosine first, put in the asymptotes, then drawing the secant is very easy. Okay, so here are our graphs. This is y equals secant x. The period is 2 pi. It is one upper and one lower segment. The domain is all x except odd multiples of pi over 2. In other words, the places, again, this is a reciprocal of cosine, so the places where the cosine would be 0. The range, it's kind of weird. It's negative infinity to negative 1 and 1 to infinity. So it's got a blank space in the middle. The symmetry, it is even. For cosecant, the period again is 2 pi. This time the domain is all x except 0 and multiples of pi. That may sound familiar. Secant and tangent have the same domain. Cosecant and cotangent have the same domain. The range is the same as the range for secant, And the symmetry, it is odd, just like its reciprocal function. Damped trig functions are actually kind of cool. What you do to get a damped trig function, it's the graph of the product of two functions. And what happens is that the graph takes on the property of both. For example, if we look at x times the sine of x, well, here's the deal. We know that sine of x gives us y values between -1 and 1. So we know that -1 is less than or equal to sine of x, which is less than or equal to 1. Multiply all three parts by x to match the function we just mentioned a minute ago, like that. And we discover that we have a sine curve that's sandwiched in between the graph of -x and +x, and looks something like that. Okay, this is the actual graph of x sine of x. This is the line y equals -x, and this is the line y equals x. And you see how the curve has conformed to fit in between those two lines. It's very cool. This is an example of y equals e to the -x times the sine of 3x. These two lines represent e to the -x and -e to the -x. So you could see how, again, the sine of 3x has changed its shape in order to fit in between those two curves. This is a summary of the trig functions that we've talked about. So just if you want to pause and look over this or take notes on that, feel free. You do need to be familiar with what these functions look like. The more you can think sine and see in your mind the sine curve, the easier this is going to get for you. Here's some more. If you want to pause and look over these, do so. If not, we'll continue. So some examples. Use a graphing utility to graph the functions, include two full periods. So this time you're just going to use your calculator. I would go to the table and get some values if I were you for these. Pause the recording, give it a try, and resume to check the answer. Remember, whenever you use your graphing utility to make a graph, what you put down on paper needs to look very much like the graph you see on the screen. You have a table function in your calculator. I would make good use of that if I were you. Use the graph to solve the equation. So this time you're going to take, the easiest thing to do is to take the left-hand side and make that y1, the right-hand side, make that y2, and see where they intersect. Set your window. Actually, the best thing to do for this is to go to Zoom and select Trig. That will automatically give you a window of -2 pi to 2 pi. By the way, I did not mention this before. I apologize for that. All of these graphs should be in radians. Whenever we graph, we rarely, if ever, will use degrees for the graphs of the trig functions. And here's the first one. Sorry if I didn't give you time to pause and try it out. If you didn't and you want to try the second one on your own, go ahead and pause now. Okay, you can see where the solutions are. And you can see the solutions for secant of x equals -2 here. To verify of the function to determine whether it's even, odd, or neither. Verify algebraically. Don't worry about the verification algebraically, just check on your graph. Pause, give this a try, and resume to check your answer. Okay, the first one is indeed even. It is symmetric around the y-axis. We do have the algebraic confirmation there, but you don't need to worry about that. The second graph looks something like this. And this is odd. If you turn the graph upside down, it looks the same.